Assalamu alaikum warahmatullahi wabarakatuh. In this lecture, we are going to discuss about the signal processing part. So we have already covered the sensors, different types of sensors, their working principle. We have done signal conditioning, and now we are going to discuss signal processing. Once this is completed, then sensors and signals part of this course will be completed. So what consists of signal processing? Once you have amplified the signals after signal conditioning circuits from an analog form, for processing it in computers and microcontrollers or microprocessors, they must be converted into digital form. After processing, the signal must be converted again into analog form, for example, to drive actuators and motors. So you have to have analog signal from the sensors, you have to convert it into digital form, and once you do all the signal processing again, you have to convert it back to the analog form. So this conversion is done by digital to analog converter and analog to digital converter. So ADC converts the amplitude of the voltage current into its digital equivalent, meaning to say binary numbers, and DAC converts digital code into equivalent analog voltage. So let's talk about these things. So normally all data acquisition boards, DAQ, data acquisition boards, are equipped with ADC. Most microcontrollers also has ADC built in, but we must know which one to be used for our purposes and how to select appropriate one based on the technical specification. So what you have to see the range, meaning to say what voltage level it supports, and then the sampling rate is very important. So if your sampling rate is not matching with your signal input frequency, then you will have aliasing, which we will see later on. Then you have to check the resolution. What is the minimum level of change in the input signal you can measure? And also you have to check settling time and number of inputs and outputs and conversion method. What are the different conversion method? Conversion method may not be that critical, but how many inputs and outputs you have in your DAQ card also sometimes is very important to know. Settling time is we don't look into settling time in and itself too much. Rather, we check the sampling rate more or less. But if you want to check very deep into the signal processing, sometimes you may have to look into the settling time as well. Okay. So usually the range is maximum to minimum analog voltage that can convert up to digital to analog digital equivalent. So typical types is plus minus 5 or plus minus 10. It is basically bidirectional, so it is plus minus 5, so plus minus 10. So minimum will go to minus 5, maximum will go to plus 5. But you can have unidirectional 0 to 10 volt, which is more common in use. Uh, Sampling rate. Now, this is very important. Always you have to remember if this is a pure analog signal which is continuous, in digital signal is never be continuous. It will be like a staircase type of signal. So you do the sample. This is the sampling rate, and you hold. This is called hold circuit. You hold this value until the next sample. So you will have this staircase type of scenario. But because the sampling rate is so fast, this del t is almost very negligible, so you can actually get a good representation of the analog signal. However, if your sampling rate is not fast enough, what could be the possible scenario? We will see in next two slides. So let's say, for example, this is your sampling time, every sample, and you have the hold in between the sampling time interval. You have to hold this value, and then you go up and you hold, go up, and so on and so forth. Now, let's see if your sampling rate is not fast enough. So let's say this is your actual signal. Now, this is your actual signal, and your sampling rate is much slower, as you can see, compared to the actual signal. So you are getting a distorted signal, the deep color one, which is called aliased signal, aliasing. So aliasing effect is basically when your sampling rate is smaller, much slower compared to your actual signal original value, original frequency. According to the Nyquist theorem, your sampling rate should be at least 2 times higher than the maximum frequency present in your signal. If it is a compound signal, you have to do a frequency spectrum analysis, and you have to check the maximum frequency that is available in the signal, and your sampling rate must be 2 times, at least 2 times higher than the uh, than the highest frequency available in the signal. If it is a single signal, then you have to just get the straightforward highest value, higher than the 2 times higher than the actual frequency of your signal. Now, let me show you a few more. So this is your original signal. If you have aliasing, you are taking slower, much slower rate, the sampling frequency, so you will get a distorted signal. Okay. Now next is the resolution. Resolution is, let's say you have a 3-bit ADC circuit. So you have 0 to 0, 1, 2, 3. So, or let's say, for example, 8-bit, 8-bit. So you can have maximum division is 2 to the power 8, which is basically 256. 2 to the power 8 will give you 256 divisions. So meaning to say, if you have a maximum voltage of 5 volt and in your input signal and minimum voltage of 0 volt, so 0 to 5 is your maximum variation. But you have total divisions in your analog to digital conversion is 256. So if you have 256, so 5 divided by 256 will give you your 0.0195 volt. That is the minimum. That is the resolution that you have in your ADC. So you can minimum change that you can measure in the analog signal is 0.02 volt approximately. So let's say if it is a 3-bit, then you have 000 means 0 volt, 001 means 1 volt, 010 means second, third, fourth, fifth, and sixth, 8 volt, 8 level. So 8 level means, so each level corresponds 5 divided by 8, which is 0.625 volt. So this is 0 volt, this is 0.625 volt, this is 0.625 1.25 volt. So the resolution is 0.625 volt. So this is how you can get the resolution. Now, let's say if VT is an output of a bridge circuit of a thermistor measuring 0 to 50 degree centigrade, so the lowest temperature change can be measured, that is, which is correspond to 0.625 volt. So you have to first check. So each voltage change is basically approximately 10 degrees centigrade. So 0.625 means 10 into 0.625, which will give you around 6.25 degree centigrade change in the temperature you will be able to detect through your ADC circuit. Okay, so this is the case. So that is what is mentioned here, 6.25. 5 by 8 is basically the resolution time. The change of the voltage will give you 10 degree per voltage change will give you around 6.25 degree centigrade change. Now, if you increase the resolution, you can change even 0.195 degree centigrade change. If you have this is 8-bit. If you have 10-bit, then you can go for 0.049 degree centigrade change. So you can see if you increase the resolution of your ADC circuit, you can measure finer change in the actual variable of your sensor. That it can be temperature, it can be pressure, it can be force, or anything like that. Okay. So this is a simple resolution example that the temperature range from 0 to 300 degree Kelvin linearly converted a voltage from 0 to 2.5 volt, then digitize it with an 8-bit converter, AD converter. So 8-bit means 2.5 volt is your maximum, not 5 volt. So you have basically around 10 millivolt per step. So you have 1.2 degree Kelvin per step. Temperature range 0 to 300 Kelvin. linearly converted to voltage signal 0 to and digital 10-bit AD converter, then it will be 0.029 Kelvin per step. So 2.4 millivolt per step. In terms of Kelvin, it is 0.29 Kelvin per step. Okay, you have to understand also if there is a noise present in the system well below 2.4 millivolt, that is beneficial for us because we can get all the noise will not be able to be detected by the AD analog to digital converter. So it is somewhat filtering out the noise as well. But if the noise is in the range of 2.5 millivolt to 2.6 millivolt, then these will be also converted back into digital format. Okay, settling time means in any systems when you have the input, the output changes, meaning to say your A to D conversion changes and it goes up and down, and then it eventually it settles into a nominal value. So this is any dynamic system. Op-amp is also a dynamic circuitry system, so it will have some time to settle down as well. So how do you make actually the DAC converter? It's basically a summer amplifier and you have V1 and V2 reference voltage all the same. Then you can, and also the RF to be same value, and you vary the R1, R2, and accordingly you can get different types of voltage output based on the different switching. So let me show you one DAC converter. So basically you turn on and off different switches, digital interface, and this electronic switch turn on and off, and you have the register network, and then you have the op-amp circuit. So this is successive approximation register network for digital to analog converter. So this is the register network. You can see it is the same summing amplifier, but in this case, the voltage reference would be the same, and you have basically switch on and off. So basically, if all are on, so it is a least significant bit, then first bit, second bit, third bit, so on and so forth, until the seventh bit, most significant bit. And the register value, this if this is R, this should be 2R, this is 4R, 8R, double it up, is always getting double. And RF is your basically a known register. If it is a non-inverting input, it will be connected to non-inverting input. So basically this is the equation. So D7, this D value can be either 0 or 1 depending on the switch condition. If the switch is on, it will be 1. If the switch is off, it will be 0. So this is the general formula for any basically your digital to analog conversion. For n-bit weighted register, not ADC, this should be DAC, sorry. This should be DAC, a correction, this is DAC. It's not, and I have mentioned wrongly, it is successive approximate register. It's not successive approximate register network, it is weighted register network. So in this weighted, because why it is called weighted? Because your resistance value is getting increased. So this is for n-bit. And if we do a simple example, which we can ask you in the exam as well. So a 12-bit weighted register DAC has an RF. Previously, I have shown RF is 5 kilo ohm, and R is also 5 kilo ohm. So RF and R are same. Reference voltage is 5. What should be the value of V out if the least significant bit is on, which means basically it is the resolution. If the most significant bit is on, and if the what is the maximum value means all should be 1, and what is a particular value for 1 0 0 0 1 0 0 1 0 0 0 1, and what is a full scale range. So this is the formula for V out to be 1 over 2 to the power 11 if it is basically least significant register is only 1, only on, turned on. Let's try to see the solution. So as you can see here, this is the formula. So this is the, if 2 to the power 11, meaning to say only this is on, that all are off. So these things will be 0. So this should be only 1. So 1 over 2 to the power 11 and 5 kilo by 5 kilo. RF and R are same. 5 voltage is your reference voltage, and because it's a negative sign, so negative sign is there. So you have resolution is 0.0024 voltage. If you turn on the most significant, then it will be 1 over 2 to the power 0. So it will be minus 5 volt. Maximum value should be if all are turned on, so it will be basically around 9.9975. And full scale range is maximum minus minimum, which is 9.9975 volt absolute value, because I ignored the negative. So that's the case. Okay. Now, this is another R2R network which has the formula as such. So this is the formula for, and again, B value should be either 0 or 1 depending on which switch is on. And then this will give you, if you turn on the most significant one, and then it will be supply voltage divided by 2 half. Otherwise, if it is least significant, then it will be Vs by 16. Now we have an example of this as well. So a 12-bit R2R DAC has a VR reference voltage, or Vs is 5 volt, R is 5 kilo ohm. So what is the value of V out for resolution, MSB, maximum value, and a particular binary input and a full scale? It's same, exactly same as the previous example. So we just carry out this. So only the least significant means that this is on, so it will give you 1.2207 millivolt. And if it is more significant voltage, then it would be half of the voltage. Sorry, it should be minus. There should be a minus. And maximum all bits are on, so it would be around 4.99878. And binary input is also, you can just convert which bit to be turned on and off. And full scale range is max minus minimum. This is the case. Okay, now this is digital to analog conversion. Now let's move on to the analog to digital conversion. In analog to digital conversion, there are various ways of doing it. So we will go a little bit details on the working principle, and then we will end today's lecture. So remember, in analog to digital converter, it is always coupled with a digital to analog converter. So analog to digital conversion is coupled with a digital to analog converter. So how does it operate? Let's see. So let's say this is your analog signal, and sometimes during the measurement, you started to sample this point. So what it will do, it will have a clock and a timer. So that will cause it to increase this counter value digitally. So it will turn on and off different switches and this with the counter. So it, once the counter is going up lower to higher level, so it will basically converting this digital to analog into a value of voltage, and it will be compared with your actual set value. And then once this set value is similar to same as this one, then it will stop this counter, and you will get basically the value that is analog to the digital value of that particular voltage Vs. So this is the way of this. So you basically at every time interval you increase the counter value and you get the next closer value of the Vs until you get as close as possible depending on the resolution of Vs. Now, next one is successive approximation ADC. So in this case, what it does is basically you approximate certain value and you compare it and you get the comparison done. And if the comparison is as close as the value of the approximation, then you stop approximating. So you can see in the loop you have a digital to analog converter as well. So let's try to show you one example. Let's say you have an 8-bit successive approximation ADC. So input range is 0 to 2.55 volt. Input signal is 0. That this is the thing that you have to convert it into digital. So your 8-bit, if you have to convert, it will be like this. How to do that? Let's try one cycle of operation. So initially you clear all the registers. So now nothing is all 0. Then the first guess is 0 1 1 1. You make it all 1 except 0. So you can see it is 1.27, which is higher than the 0.55. So you turn off another bit. So you have 0.60. Still it is high. Then you turn off another bit. So you see this is 0.31. So you then turn So you increase this one by turn on this and turn off this, you get 0.47. So this is how you approximate, and you can check high low, and then once you converge to a value 0.52, you stop this process, and this is your final approximated number, which is 110 100 001 101 00. So this is your final value of the digital format of 0.52 voltage of analog value. Okay, we have some other parallel encoding. So in this case, what we do is basically you have n-bit ADC, and we get each, you have comparators, and each looking after voltage, and the register generates trial values and compare it with the input values. Now, so you have multiple comparator, and you can do simultaneously all the things compared. And once you turn on and off this MSB to LSB, and then you finalize that which is the value you should look for. So this is a comparison. So you have multiple comparator in this case, not like other case. And then you have single ramp. In this case, you have the capacitor value. You turn on and off different capacitor value, and accordingly you check the voltage. Again, you do the comparison, and you can see this is the comparison. And finally, you will get the n-bit output values of your analog voltage. I think that is all for signal processing. Hope you have enjoyed. And now, once, because we have finished sensors and signals, now we are ready for our first assessment, which I will announce in the Moodle and the Telegram channel, inshallah. Thank you very much. Assalamu alaikum wa rahmatullahi wa barakatuh.